Let's get right to it with 6.3. How does momentum determine the motion of a system's center of mass? By the end of this, you're going to be able to calculate the velocity of a system's center of mass and determine what forces change the motion of a system's center of mass. Looking at the vocabulary, we have center of mass, which is a special location for a system where the system would balance if it were set on a fulcrum. Fulcrum is also a vocabulary term. Fulcrum is just the pivot point. If you think about a seesaw with a triangle in the middle and then you get the balance, it's the little triangle. That's the fulcrum. That's the thing you are balancing on. This is a review, so you can go back to lesson 3.3. If you need more review on center of mass, go through that lesson in its entirety because we're going to kind of blow through this. So the center of mass can move. This is important, and it's related to momentum. If any object of a system is moving, then the system's center of mass can itself be moving. The velocity of a system's center of mass is determined by the total momentum of a system. So as we're going through this, think about two cars coming together, crashing, or maybe one car catching up on the other one. What's happening to the center of mass? The momentum of a single object is mass times velocity. The velocity of a system's center of mass can be found using the equation the net system momentum equals the total system mass times the velocity of the system's center of mass. Here's our CM right here. The red car is twice the mass of the blue car. Did you notice the center of mass is always twice as far from the blue car? Because it's half as much mass. The blue car is half as much mass as the red car, so the center of mass is going to be further away from the lighter piece. It's going to be more attracted to the heavier side. It's going to gravitate towards it. Find the center of mass using, there you go. Find the center of mass velocity using momentum principles. Before the collision, the momentum of the system is mass of the blue car times the speed of the blue car plus the mass of the red car, which was at rest. So all of that total equals 6 kilograms times meters per second. We're going to use this to find the center of mass velocity. So the net momentum equals the total mass times the center of mass velocity. Total mass, the net momentum. You get it, right? Not bad. This key equation right here, you gotta have that stuck in your brain because it's not going to be on your equation sheet. You just have to understand that that is you can think of it as the total momentum for the entire system, right? And the entire system is moving with one speed if you look at it as a whole unit. That whole unit speed is the center of mass speed. So you have to find the total momentum involved. If the red car were traveling in the opposite direction, remember this would be negative because momentum is a vector and you can have a negative velocity because velocity is a vector. Center of mass velocity does not change even during or after the carts collide. This is because momentum is conserved during the collision. Conserved momentum means that your net momentum is constant. Because net momentum stays the same before, during, and after the collision, the velocity of the center of mass will stay the same.